Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Welcome back. We're in AP Physics 1, still in Unit 2. We promised that it would be the last video of this unit, maybe 3 videos ago, so we're still in Unit 2. But we're doing centripetal acceleration and really centripetal motion in general, centripetal forces and centripetal acceleration. We just had our unit that was kind of the intro on concepts on centripetal acceleration and what is a centripetal force, what forces tend to be centripetal forces. So we've had that video, and we've had the yo-yo video. So now we're on what's called the conical pendulum. All right, so we've got our Isaac, our little bunny we named after Isaac Newton here, who keeps featuring in some of our videos. And we have this mass hanging from a string of a length L. So this is going to be from where I'm holding it to the length of the string. So that's going to be L. But this time, in an earlier video, we swung it horizontally, my colleague Beth. She also swung it vertically like a yo-yo and had 2 yo-yo examples. Today we're going to swing it at an angle, and it's called a conical pendulum. The Isaac, if you can see this, Isaac is still going in a horizontal circle. However, there's now an angle of this string. It's not vertical, swinging vertical, and it's not swinging horizontally. All right, so it's called a conical pendulum when this happens, and we're going to do this problem on conical pendulums today. So let's just get started. I have it kind of drawn out here where I have a length of a string. I have the mass, which was Isaac's mass. I have a theta. There's an angle now. As we were swinging that, there was an angle, a theta that was holding constant, and we're going to swing Isaac at a constant velocity around this circle. All right, well, first of all, we know it's circular motion, so that's your big hint that you're going to centripetal forces. All right, and it's also a big hint that you should always, we're just going to start with Newton's second law for centripetal forces. All right, so that's where we're going to start, because it's always a question as we're getting more and more equations and the problems are getting longer and harder. What equation do I pull out of my little equation tool belt? All right, well, my big hint here is it's circular. Okay, so we've got the sphere with mass m attached to this string length L. The swing, it's going in a horizontal with constant speed angle theta. Okay, now what are they going to ask you? They're usually going to ask for an expression. They want an expression for that velocity. All right, and they're going to tell you it can only be in length, it can be in theta, it can be in constants, g. Sometimes they'll tell you it can be in mass if you want. But these are really the only expressions, the only variables you can have in this expression. Okay, so let's get started. We need a free body diagram. This is dynamics. Anytime you see dynamics, centripetal motion, you need a free body diagram. So I'm going to do it from this position right here in FBD. All right, so I have my Isaac, my mass. I have tension that is going along that string, tension. And then I have force due to gravity that is here going down as it always is. Okay, so that's your free body diagram. Okay, but here's the deal. Where is center seeking forces? It's towards the center, right? Centripetal forces are center seeking. So we're looking for a force that is towards the center of this horizontal circle. Okay, well, I don't see any horizontal forces just right away. But, and again, don't do this on your free body diagram because we don't like to put components on our free body diagram, but I'm going to do it over here. I have my force of my tension. I'm just kind of redrawing this. It has an x component. That force of tension in the x is right here. And then it has this force of tension in the y that's here. All right? Now, the force of tension, and it should have been the same length as this force due to gravity in the y. The only centripetal force I have, only force that is center seeking, that is moving this thing in a circle, that is towards the center, is this force of tension in the x direction. Okay, that's it. And if this is theta, remember, they're not giving you this theta. They're not going to give you this theta in a pendulum. They're going to give you this theta with the vertical. So it's up here. So now my force of tension in the x is opposite that angle. That means that sine, right? This force is opposite the angle. So that's going to be, if we did sine theta equals the opposite, which is that force of tension in the x, over the hypotenuse, which is force of tension. I'm going to multiply that. Sine theta equals that force of tension in the x. All right, so I just figured out what my centripetal force is, because it's the only one that's horizontal, that's in the plane with the circle. Force due to gravity is perpendicular to that plane, and the force of tension in the y is also perpendicular to that plane of the circle. So I'm just going to put this in. So my only centripetal is that force of tension, sine theta, because that is, actually let me not skip that. Let me go ahead and put that this is the force of tension in the x, equals m. Now remember, centripetal acceleration is v squared over r. We've got constant velocity, because look, they want an expression for velocity. Keeping centripetal acceleration in here is not going to help me with that, but subbing in this value for centripetal will get me my velocity in this equation. All right, so we're there. My force of tension in the x we just did, that's force of tension sine theta equals mass v squared over r. That's a V, not an R. All right, perfect. And you're like, oh, okay, I multiply by R, divide by mass, and I have my expression for velocity. Ooh, this is easy. Okay, well, not so fast. Look, we can't have force of tension in this formula as a variable in our expression. So we are going to have to figure out what to do with this force of tension. So here's what's going to happen. We're like, well, I don't know. The only other thing I can do is sum forces in the y. They didn't give me the force of this tension. It's going to be in my expression, but they don't allow it. So what else do I do? What do? I'm going to sum forces in the y. So summing the forces in the y, and remember this Isaac is not moving in the y direction at all. He's moving in a horizontal circle. He's not moving in the y direction. So the acceleration in the y is 0. And oh, I have two forces in the y. I have that force of tension in the y, because that tension, that's a northeast component. That means parts in the north and parts in the east. The part that was in the east was the centripetal. The part that was in the north, that's a y force, right? In the y direction or vertical direction. And then I also have this force due to gravity here that's in the vertical. Up for force of tension, that's up, because that's a north component. Force due to gravity is south. So we're going to have force due to tension in the y minus force due to gravity equals 0, because acceleration is 0. Any mass times 0 is 0. I'm going to solve for that force of tension in the y, and I get force due to gravity. We know that is actually mg. And you're like, oh, okay, where are you going with this? Okay, I need an expression for force, for my tension force. If I can find an expression, look at this, I'm getting closer to finding an expression for tension that I can sub in here. So then I'm going to eliminate that tension force in my variables in my expression. So my force of tension in the y, look, here's the angle. If I try to blow this up one more time, this is my force of tension, and then this is my angle theta. This is my force of tension in the y. That is adjacent to that angle. All right, so that would be cosine. Cosine theta equals the adjacent side force of tension in the y over my force of my tension. I multiply that force of tension times cosine theta is going to equal that tension in the y. So I'm going to plug that in right here. So my force of tension cosine theta equals my y, I just subbed that in, equals mg. All right, I'm going to find that expression. I'm just trying to find an expression for tension force so I can plug it in right here. All right, so now I'm going to divide by cosine theta. Both sides divided by cosine theta, and I get an expression. I have now this expression that I can take and put in right here. And I'm going to do just that. Ft, that force of tension, is mg cosine theta. I still have a sine theta, though, that I'm multiplying by. and then mv squared over r. Okay, well, I'm looking at both sides of the equation. Mass, as we say, mass was brought to the party. Both sides brought mass to the party. So cue Miley Cyrus's Party in the USA, so we could play that in the background in our heads. Mass is gone, and sine divided by cosine, hopefully you remember this from math, that's tangent theta. Sine theta divided by cosine theta is equal to tangent theta. So I have g tan theta equals v squared over r. I multiply r over, and I get r g tan theta equals v squared. I take the square root, and I get square root of rg tan theta equals v. I go back up to my expression. I have theta and g. I didn't even need mass, it canceled out, but I'm like, oh no, we need length. And I have it in radius, because when we did centripetal acceleration, it's v squared divided by r. So now I've got to come up with an expression for r that has length in it, that's related to length. So now I'm going to go over here so you can see this. If this is the length of my string, and I can do this because they're both in the same unit, we're both talking about lengths. Here is my r, which is also in meters. And here's my angle theta. All right, well look, that is opposite theta, r. That's sine. So sine theta equals opposite side, which is r, over my hypotenuse, which is L. And now look, I know L sine theta equals my radius. The length of my string times sine theta equals my radius. I can now plug that in, this whole little expression for r right here. And voila, we get the final answer, which is this, that L sine theta times g, because I just plugged that in for r, tan theta equals velocity. Now, I could plug in numbers. If I had length was 0.5, theta was 30 degrees, and my g, of course, is 9.81, then I would get a velocity of 1.2 meters per second. So you can use this. But really, most times, or oftentimes, they want that expression, and they won't give you numbers, or they want the expression first and then the numbers. All right, so let's review this. We did centripetal motion. We just went there first because we knew it was moving in a circle. We used that centripetal acceleration was v squared, that velocity squared, that constant velocity squared divided by radius, because they want an expression for velocity. So I had to sub that in. I knew that my centripetal force, and it's positive because it's center seeking, and remember positive is always center seeking. If it's outward, then it's going to be negative, but towards the center is positive, so that's going to be a positive tension force in the x, because it was the only one that was horizontal, the only force. Force due to gravity was perpendicular. The force of that tension, that y component, was perpendicular. That's the only centripetal. And then we got some expression, but we couldn't have tension force in our expression. So then we've summed the forces in the y. There were two forces in the y. One was north, one was south. And we came up with an expression for that tension force to plug in right here. And then we had to deal with r. And we had to find r, and we had to find r in terms of length to sub in. And you got L sine theta g tangent theta equal, the square root of all that equals velocity. And that is how you do a conical pendulum problem. I hope that helped. I hope you enjoyed watching. If you like this video, please like it. If you want to see more of what we're doing going to be doing every unit. Please subscribe if you'd like to see more and share with your friends. Thank you, and happy physicsing.